It's time to move into the TCP/IP protocol, leaving OSI behind and actually as a foundation that we're going to continue to build on as we move throughout this series and move into TCP/IP. TCP/IP is the protocol of communication that we used on networks around the world. And we're going to talk about as we go through this, number one, how OSI and TCP/IP relate. We just finished talking about the OSI model. How does that relate to TCP/IP? We'll then look at the two address concept. What I specifically mean by that is why do we need two addresses on every packet that we send? A MAC address and an IP address, to give an example of those. We mentioned that in the OSI video. We're going to fully expound on that here. We'll then look at the IP address format, what IP addresses are designed to do and the pieces of them, the default classes, class A, B, and C addresses, and finally, the difference between public and private addresses. So here we go. Let's begin by talking through a commonly confusing point, as in how the OSI model and TCP/IP relate. If you're going through these videos in order, you just finished looking at a video that explains communication through the eyes of the OSI model. But how does that relate to TCP/IP, which is what we use around the world today? Well, this is a little known fact. The OSI model was never meant to be just a model. It was a competing standard to TCP/IP back in the days of the 70s. It was actually a competing protocol that people developed called the OSI protocol that they were kind of vying for who would win. You know, is it going to be TCP/IP? Is it going to be OSI? What's going to win the competition? Well, we know the story today is that TCP/IP ended up winning, and it's kind of ironic because OSI was actually a little bit better of a protocol. The reason that it didn't take hold was because its addresses were far too complex. It had too many addresses, if you will, because it used hexadecimal and it just had a ton of addresses that could be used. And people looked at it and said, well, why on earth are we going to end up needing that many addresses? Now we can look at it today and say, oh man, I wish we had some more addresses, because nobody had any idea how fast and how big the internet would grow. And it's kind of funny that the next version of TCP/IP, called IPv6, looks familiarly like the old OSI protocol. So OSI, the OSI model, is still used as a way to explain network communication and a way for standards to unite and all the things we talked about the OSI model in the previous video. But the TCP/IP model, the one over on the right-hand side, is what's typically used today in communication. A lot of people call that the DoD, the Department of Defense model, because it essentially maps up to the OSI model and boils the top three layers down into one big application layer. That's because all of this stuff happens typically before it ever leaves the computer. The routers and the switches don't ever look up there at that application layer stuff or all this stuff. This is only seen by the operating system, Windows or Linux or whatever operating system you're using. The transport layer ended up passing through and stayed as the transport layer. The network layer passed through and became the internet layer. These two were boiled down into one layer called network access, because they figured it's pretty much all the physical stuff, things physically accessing the network. So that is the Department of Defense model that's used to describe how TCP operates. And it's kind of ironic that TCP/IP is all we use to communicate nowadays, but I would say by far the OSI model is used far more to describe network communication than the TCP/IP model. So if you only have enough brain space to remember one, remember OSI. Now, the OSI model may be a way to describe how networks communicate, but TCP/IP is how it actually happens. That's the protocol that we use today. Now, the first thing first with TCP/IP is we need to understand that it's not just one protocol, but it's a suite of protocol that makes things happen. Think of it like this. When I think of Ford, the car and truck manufacturing organization, I don't think of just one company. I think of a suite of sub companies, meaning there's over in Detroit, Michigan, it's where I was born. You have all of these different vehicle manufacturing plants where they have the assembly line, and there's some groups that work on the car doors, and there's some groups that work on the engines, and some groups that put the axles and the wheels on the vehicle. And they all tie it together and put it on a big truck that's its own company, and that truck transports all of these vehicles to the distribution center or the car lot where you go to and speak to a Ford car salesman, part of the Ford package, but definitely a far different function than the people in the manufacturing plant putting the car doors together and things like that. He says, well, yes, 21,000 would be a reasonable price for this vehicle, and you say, well, thank you, sign the vehicles, you're out. After that, to do maintenance on the vehicle, you have all of these different Ford maintenance shops that you can go to make it happen. So when you think of Ford, you may think of one company, or if you really think about it, it's a suite of companies. And in the same way, TCP/IP is a whole suite of protocols that makes network communication happen. You have down here, you can see the network layer or internet layer in the TCP/IP model. We have IP, which is responsible for addressing packets to help them get from their source to their destination and back. You have up here at the transport layer, sometimes TCP/IP labels that as the host-to-host transport layer. Transport layer is much easier. You have the TCP and UDP selector or the choice that allows reliable or unreliable communication. Up here you have the actual applications that make it happen. Things like Telnet, FTP, SMTP, which is responsible for email. All these different application layer protocols that begin and start the whole network communication process. So as a application begins to communicate across the network, it's very similar to building a car. It's like, we want to build a car. Well, let's start by putting the guts in the car. That's the application. Then how are you going to transport it to the dealer? What destination are you going to? All of those pieces come together to make network communication possible. What I want to do here in this video is focus on one subcontractor piece of TCP/IP, and that is IP. That layer 3, the network layer of the model, or the internet layer, depending on what model you're looking at, that defines the source and destination IP address. Now we will have probably, I'm thinking, just thinking ahead a little bit, probably 2 or 3 full videos dealing with nothing but how you can design these IP addresses and make them operate correctly in the way that they were designed to be. What I want to do here is just get a base level understanding of how IP addresses function on your devices. First thing is that an IP address is 4 numbers, or a lot of people will call them octets. 4 octets, each number from 0 to 255. Each one of these that I'm underlining here is an octet. They can be anything from 0 to 255, and we have up to 4 of them. Now that gives us the opportunity to have I don't want to throw out numbers like trillions, but a whole lot of IP addresses that are available. And the funny thing is that we are running out. If we were to give every device that could have an IP address, we would be out of IP addresses 10,000 times over. And that's why they're creating a new version of TCP/IP. Oh, don't worry. When we get into the new version of TCP/IP, these concepts don't go away. So I don't want you thinking, I can skip this. The new one's coming out. It's very similar to the way this works. So when you're talking about an IP address, it is always combined with a subnet mask, always, and typically combined with a default gateway. So you can see that I have an IP address right here, 172.30.5.82. I have the subnet mask 255.255.255.0 and a default gateway, I just have GW there, of 172.35.1. Let's keep that in mind. We'll come back to that a couple times. The subnet mask dictates what portions of the IP address represent the network and the host. I'm going to do something right here. I'm going to draw a line. Just like that. At this point, you can think anytime that you see a 255 in the subnet mask, that represents the network. Anytime you see a 0 in a subnet mask, that represents the host on that network. So look at this example down here. I have two computers, one of them 172.35.82 and the other is 583. Now looking at their subnet masks, notice that they both have the same first 3 octets of their IP address. Right there. Forgive my squiggly underlines. That tells these computers that they are on the same network. They know that if they want to reach each other, they can do so just by communicating back and forth to each other. It's not a big deal for them to communicate. They don't need to go through routers at all. They will just, communicate directly together. Now, the host portion, I forgot my T there, the host portion identifies who you are on that network. Notice that this is host 82 and this is host 83. When it comes to IP addresses, when you have all sorts of devices plugged into the same switch or the same hub, they are considered on the same network. And they must start with the same octets of their IP address in order to communicate. Meaning, if I were to change something here, and I said, you know what? I don't want this guy on the bottom to be 172.30.5.83. I want him to be 172.31.5.83. Just like that, this host and this host can no longer communicate. They are completely cut off from communicating because they believe that they are on different networks. So, what's this whole different networks concept? Well, you're supposed to split up your networks in a way that can best control. I'm thinking in my mind, boy, I could go so many different directions right now. Let me just say this. It is best to break up networks in your organizations as they get larger and larger, because eventually they will reach a point where they are so large that it gets so busy on that network that nobody can speak anymore. And that's really dealing with this concept of broadcast traffic. We'll talk more about that later, but that is one of the reasons that you will split networks into a one single network into multiple networks. Let's do this. I'm going to take you on a practical journey through IP address communication, and then we'll come back here and hopefully that will explain this a little bit better. Yes, this picture will work much better for explaining how this IP address concept and this network concept ties together. Now, you can see the title of this slide is Understanding the Two Address Concept, which is something that we touched on in the OSI video, just last video in the series. And I want to expound on fully right here to fully understand what this means. Let's say that over on the left-hand side, you have a home network. Home. And at the edge of your home network, you have this Cisco router because you have a lot of money and can afford to have a Cisco router running your home network that connects you to the internet via DSL or cable modem connection. And inside of that home of yours, you have two computers. This guy right here, 10.1.1.10, and this guy right here, 10.1.1.11. Now, in this picture, I want you to make a big assumption, and that is that we are using the subnet mask 255.255.255.0 everywhere in that network. What that means is the first 3 octets represent what network you're on. The last octet represents what host you are on that network. So essentially, I could say this by saying you are host 10 and host 11 down here on the home network. Over here, once we leave that network, notice once we leave your home, whoops, I'm undoing my subnet mask up there. You are moving into a new network over here, the 10.2.2 network. And once we leave that internet service provider's connection, we are moving into yet another new network, 10.3.3 to 10.4.4 to 10.5.5. So anywhere that you see a router in the picture marks a dividing line between networks. Because here's the statement. A router is and represents multiple networks. Every interface of a router represents a single network. You can never have two interfaces of the same router. So you had something like that. Can't be done. Can't have two interfaces of the same router plugging into a network. So Here's the story. You are sitting over here on 10.1.1.10, and you want to share some files over here with 10.1.1.11. Just a simple file sharing operation. So what I would do, if we'll say I just want to copy some files down there, I would say in my whatever application I'm using, copy, we'll say file.zip, some file, to 10.1.1.11. Now, behind the scenes, what my computer does is immediately compare its address, 10.1.1.10, to that address, 10.1.1.11. It says, okay, well, I am 10.1.1.10, and I'm trying to get there. Are they on the same network as me? Well, looking at the subnet mask, I start with 10.1.1.1. They start with 10.1.1. 10.1.1 if I added too many ones there. We both start with the same network, so I am assuming that 10.1.1.11 is on the same network as me. So the next step that I'm going to do is yell. Literally, this is a computer's way of yelling to the network. An ARP. ARP. I think of it like a dog. A dog barks. It gets everybody's attention. ARP, ARP. It stands for the Address Resolution Protocol. It is always a broadcast message, meaning that every single computer inside of your home is going to receive that. So when 10.1.1.10 wants to reach 10.1.1.11, it's going to send out an ARP saying, hello network. Remember, this is a broadcast, so it's stepping up to the microphone. Hello network, I am trying to reach the computer named 10.1.1.11. Can somebody on this network tell me who that is? Now, everybody gets that, and maybe we've got this router who is 10.1.1.1. It receives it. It doesn't respond because it's not 10.1.1.11. Some other computers get it. They don't respond. But this guy receives it because it's a broadcast, and it says, oh, that's me. Somebody wants to talk to me. So I will respond back to that ARP message with my MAC address. Now we're starting to move into this two-address concept. This 10.1.1.11 computer will respond back and say, hey, here is my MAC address. I am, 00A0, blah, 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 whatever 12-digit MAC address. You can see my format up here. You can either write it as 2 digits, colon 2 digits. That's how Microsoft does it. Or Cisco does it, 4 digits, colon 4 digits, and so on. So that computer responds with this MAC address. This computer then starts transmitting data to that MAC address. It's kind of weird to think of it this way, but computers never speak directly to IP addresses. They can't do it. They only speak to MAC addresses, or let me group that a little broader and say layer 2 or data link layer addresses. Sure, inside of that packet, just like we saw when we looked at the OSI model, is the source and destination IP address, but it's trying to talk to a MAC address. So when your file.zip file begins to copy, it will come from this MAC address and copy over here to that MAC address. Whew. A lot of arrows, a lot of scribbles on there. That is how local communication using IP happens, meaning it's all local on your network. Now let me expand this a little more and talk about how it would happen now from the same host, 10.1.1.10, to this server over here. Maybe that server is your file server, and you want to store that same file, file.zip, on the corporate file server, which is across the internet, many routers away. Here's how it happens, and be sure you catch this, because this is the core of all network communication. I, on my computer, say I want to copy to 10.5.5.100. So I issue my copy operation to copy file.zip. Immediately, the computer looks at its IP address and says, okay, I am 10.1.1.10. They are 10.5.5.100. Looking at our subnet mask, 255.255.255.0, I can recognize that they, boop, are on a different network than me. I am of the 10.1.1 network. They are of the 10.5.5 network. So I immediately know that I cannot use my ARP protocol. That's one of the sub protocols of TCP/IP. I cannot ARP for 10.5.5.5 because ARP is a broadcast message, meaning everybody gets it. And one of the sole functions of routers, if you look at a router's resume, item number one on that resume is a router stops broadcasts. That's their role. That's their function. Routers tie together the entire internet for good reason. If broadcast from my home were to travel unbound around the world, I mean, people, anytime I would boot up my computer, a broadcast would happen. And by the way, broadcasts happen all the time. Anytime I want to communicate on the network, a broadcast would happen. Anytime I want to go to a website, a broadcast would happen. And combine that with my computer and the billions of other computers that are around the world, and you would just have this massively overwhelmed network with broadcasts going everywhere. So my computer immediately realized when it looks at that destination IP address, it's like, hey, that's not on my network. I am going to have to find some other means to get there. Remember what I said on the previous slide? I said with every IP address or with every device, you typically have an IP address. You will always have a subnet mask, and you'll always have an IP address. And typically you will have anyone remember the third piece? Default gateway. The default gateway is the IP address of the router that you need to go to when you don't know how to get there. So follow this. Here's the scoop. I am 10.1.1.10. I am trying to reach 10.5.5.100, but I know that I can't ARP for it because I know my ARP would die right there because it's a broadcast and it's not going to travel around the world and reach the server to find out what the MAC address of that server is. So what I will do is I will ARP for the MAC address of my default gateway. The computer knows who its default gateway is because I typed it in there. When you set up your computer, you put in IP address, subnet mask, and your default gateway. So it's going to say, okay, I need to reach 10.5.5.100, steps up to the Ethernet wire and says, hello, who out there is 10.1.1.1? It's not looking for 10.5.5.100. It's looking for the MAC address of its default gateway. The default gateway and this guy, because it's a broadcast, get it, but only the default gateway responds and says, hey, buddy, my MAC address is 00B1, 9911 5511. So it gets its MAC address back. This is the two address concept. When this guy is putting its packet together, give him a face. When he's putting his packet together, it will come from a source IP address. Well, let me have you fill in the blank. Think about this as I work through this. The source IP address is going to be who? Him, right? 10.1.1.10, because that is where I'm coming from. The destination IP address will be who? The server. That is who we are going to. I'm not trying to get to my router. I'm trying to get to that server. This is the two address concept. We now move down here. The source MAC address is going to be who? Me. I'll just put me there because I didn't give this guy a MAC address. We'll say 0011 blah blah blah, some giant MAC address. So it'll be 0011, the MAC address of that computer. The destination MAC address will be who? The router. I think I gave him the address 00B1 da 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 da. Go down that list. That will be this guy right here. So when the packet is sent, it will be received by this router. The router will look at it and say, oh, that's my destination MAC address. So he's trying to get to me. I get that. But when I look at the destination IP address, I realize that he's not getting to me at all. He's really just trying to go through me to reach some server down the line. So what's the router do? And this is stepping into some deep TCP/IP stuff. The router looks at its TCP/IP routing table and says, okay, well, I can see based on my routing table that I'm not plugged into the 10.5.5 network. I'm plugged into the 10.2.2 network, but my routing table tells me to send it to this person because they are advertising that they have some way to reach 10.5.5.100. Now, don't die on me here. Check this out. Here's what happens. As this goes through that router, it strips off, literally tears off all MAC address information that just came from the LAN. I mean, if we could, visually zoom in and look at that packet, the router grabs it with its metal virtual hand and goes and tears the MAC address stuff off and replaces it with its new source MAC address for this line and the new destination MAC address for that neighbor. Now, every interface has a different MAC address, just like every interface has a different IP address, and that will now come from this source going to that destination. Notice the IP addresses do not change. Think of it this way. If you were taking a road trip, think of some very far away place, like thousands of miles away. Like I'm in Phoenix, Arizona. Imagine I was going to Toronto, Canada. There is no way I could drive straight through from Phoenix to Toronto because A, my car would run out of gas, B, I would probably fall asleep, C, my bladder would explode. So with all these factors, I would have to lay out a better plan. I would have to say, you know what? I'm going to take a pit stop in Flagstaff, and I'll stop there. But remembering all along that Flagstaff is not my destination, it's just a pit stop. I mean, if these IP addresses change, if my original source and final destination change, the packet would get lost. Just like if I got to Flagstaff and I'm like, where was I going? I don't remember. I'll just kind of settle down here in Flagstaff, in some little small town along the way. So you can't change the original source and final destination, but you can change your waypoints. Every single router that you go through tears off the original source and destination MAC address. These will go away as soon as that link is completed. These go away as soon as this link's completed. And it will replace it with the hop-by-hop address that allows it to communicate on that specific network. Finally, when you get to the destination server that you're trying to reach, it will become this source MAC address and this destination. But all along, the server will see that it originally came from 10.1.1.10 and is finally going to him as the server. So when he responds, you can see he's going to be using that as his destination. I just took a step back from the screen and kind of took in the screen as a whole. I'm looking at all this scribble and how do you learn anything? But look at that. Hopefully it was a build by build process because that's a messy looking screen. But that is the two address concept. That is how network communication happens. Every single device has its MAC address and its IP address it uses all along the way. Whew, that's some heavy stuff. Why don't we lighten it up a little bit as we begin to wrap up this video? Just two more things I want to talk to you about. Default address classes and public and private addresses. When the powers that be created TCP/IP, they designed 3 classes of addresses that would be usable on our networks of today. Class A, Class B, and Class C. Now the concept of this was fairly simple. They did not envision the internet being as big as it was today. So they said, well, a Class A network will have the default subnet mask of 255.0.0.0. So for example, you see that I have right there 10.5.1.1. With the default subnet mask 255.0.0.0, that means that anything starting with 10 represents the network, and all 3 other octets represents hosts on that network. So for example, if I had 10.90.20.111, that would be considered a host on the same network because they just both start with 10. That's a Class A network. Now just to give you an idea, if you use Class A subnet masks, you will have 16,777,214 hosts available to you on one network. Let me put that in perspective. Cisco recommends that you do not go above 500 hosts per network, because if you do, the broadcast traffic starts to get a little unruly and it can actually affect the performance of your PCs that you attach to the network. Come back into perspective here. 16,500,000. We have slightly exceeded Cisco's recommendation for the maximum number of hosts per network. So you can see that Class A networks just won't do. We have to do something to them in order to make them functional. And that leads into a big topic known as subnetting, which we'll talk about a little later in the series. Class B networks are networks that have subnet mask of 255.255.0.0. For example, you can see right there 150.51. Why do I rewrite the example that I just wrote a moment ago? Right there, 150.51, 233.1. This represents the network. This represents the host. So we have two octets for the host. That leads to about 65,000, somewhere in the 530 six, I believe, hosts per network. Don't quote me on that exact figure, but you can see, again, slightly exceeding the 500 hosts per network. So if we use Class B, we're going to have to do something to them, known as subnetting, to make them really usable in a smaller scope of devices. Class C networks have the subnet mask 255.255.255.0. Example of that, 220, 150, 63. That just means this represents the network, and this represents the host on the network. This one gives you 254 hosts, usable hosts per network. Now you can see that's why this subnet mask is very, very popular. It's a very reasonable number to work with. So Class A, Class B, Class C. The big piece I want you to make sure that you catch is how to tell what's what. I'm circling them right now. If you just look at an IP address, you can tell what class it is by default. Meaning if you just go on your computer, try this. You're sitting on a computer right now listening to me, open up a command prompt and type in the command ipconfig. If you're using Windows Vista, you'll get a lot more stuff than you bargained for. But I can see right here that two of my network cards, 192.168.159.1 and 151, are using Class C IP addresses. I know that because the first number of that IP address is 192. I look back over here and it says first octet is 192 to 223. I also see that my computer, which, by the way, has a lot more network cards than most, has another network card with the IP address 172.30.2.50. That is a Class B address because it starts with a 172. And I look right here, Class B is 128 through 191. Finally, Class A, 1 through 126. Now, you first might look at that and say, well, you forgot one. The 127 range is missing. Well, that's because any address that starts with 127 is reserved for loopback, which we'll talk about on the next slide. These are the ranges of usable IP addresses, things that you can actually assign to devices. Now, when we get into subnetting, it's going to be a huge bonus to you. Did I say bonus? I meant foundationally recommended understanding. I mean, you got to know those numbers. Make sure you know those numbers because when you get into advanced IP addresses, you'll need to be able to identify what class an IP address is from just by looking at the first octet. Last piece of TCP/IP we'll talk about here is the difference between public and private addresses. Public addresses are IP addresses that are usable on the internet and on internal networks. Meaning, if I want an IP address that is able to surf the internet and access the internet and have people on the internet access it, for example, maybe I have a server or something like that that I want people on the internet to be able to send stuff to or receive stuff from, I would give it a public address. Now, how do you get public addresses? Well, you typically link up with a service provider. The service providers went to the government and purchased a block of IP addresses that they now own. And you would go, let's say, to a service provider, we'll say Sprint or AT&T. Let's use Sprint. And you say, Sprint, I would like a Class C block of public IP addresses to use in my organization. Sprint would say, okay. Well, as long as you're with us, you can use this Class C block. We'll say 200.1.1. Anything that starts with that, and you will pay us $5,000 a month to do so. You say, ouch, and then you give them the money. They give you the public IP addresses, and you can use them. Now, the private addresses are addresses that are only usable on internal networks, meaning that if you have a private address, that address can only directly communicate with stuff on the internal network, servers within your company, other laptops, you can have a webcam conversation with somebody in the cubicle farm next to you using your private address. But that address cannot communicate directly onto the internet. There are three ranges of private addresses available to us: Class A, B, and C ranges. Those ranges, again, just like the last one, I would recommend being able to recognize off the top of your head. So if you're able to see one of them, you can immediately know if an organization is using public or private addressing. 99% of the time, if you're in an organization, they will be using private addressing. I'll say 99.9% of the time. Now you might say, well, if that's the case, if everybody's got private addresses, then how does anybody surf the internet if they can't use those addresses on the internet? Whew, that's a good question. I'm glad you asked. That's moving into a concept known as NAT, which I was planning on saving till later, but there's been so many slides I've gone through at this point where I'm like, man, I wish I could talk about NAT. So let me just give you the basics. NAT allows people to share a public IP address. So, for example, let's say that you have a router at home that you use to access the internet, just a little Linksys router. That Linksys router links up to the service provider and gets to use one of the service provider's public addresses, we'll say 200.1.1.10, as long as it's connected to that service provider. When you pay for a high-speed connection at home, you're not only paying for the line that comes into your house and gives you the connection, but you're paying to use one of that service provider's public IP addresses. Now, all of your devices inside of your home network use private IP addresses. We'll say this one is 10.10.10.10, and this one over here, this computer that just appeared, is 10.10.10.20, and so on. And when they go through that NAT router hides the public IP address and makes it appear as though they're coming from its, did I say hide the public one? Hides the private IP address and makes it appear as though they're coming from that router's public IP address. And that is the same thing that corporations all around the world do to conserve public IP addresses. I mentioned early on that if every device that exists in the world were assigned an IP address, we would have run out 10,000 times over. So what we have is this ability of NAT to allow many, up to thousands of PCs to share a single public IP address. That's how people that use these IP addresses inside of their corporations, that's how you, who use those inside of your home, have the ability to access the internet, even though you are using what's considered as an address only usable on internal networks. Now, the last two ranges is the loopback range, which is used for testing, very rarely used actually. 127 dot anything is considered loopback. And then there's an auto configuration range, 169.254 dot anything. That's if a host cannot get an IP address. You either forgot to assign one and it can't get one from something known as a DHCP server. It's going to just make an address up known as 169.254. Those addresses can't really do anything. It's kind of like, help, I need an IP address. Give me something that I can use. This can only communicate on its own local network. You now have a whole bunch of TCP/IP stuff sitting on the plate in front of you. And I want to make sure you understand that this series does build on itself. Meaning, as we go through, we're going to keep coming back to that plate and pulling off pieces and adding a little bit more. Just because I want to make sure that as you go through, there's probably some stuff that was in this video and maybe even the last video where you're like, I really get that. I understand that. I'm good to go. And there may be some stuff where you're like, I see what it is, but I don't know the how of why it's used. It's like spaghetti sitting on that plate in front of you without any sauce. It's kind of bland. Don't worry. We're going to continue to build on that as we continue through this series. And for instance, public and private IP addresses. We'll be using that and implementing that in many ways as we continue on. But what we talked about in here was how the OSI and TCP/IP models and protocols relate. We found out that OSI wasn't just a model, it was a competing protocol back in the day. We then looked at the two address concept, where we had the MAC addresses or layer 2 addresses and IP addresses at layer 3. We talked about why we need those addresses and how they're used in communication. We then looked at the IP address format, the 4 octets with a subnet mask and a default gateway that combine to get networks communicating. We finally looked at the default IP address classes, class A, B, and C. Be able to identify those by the first octet, and you should be able to look at an IP address and say that is a class B address. And then we looked at public versus private addresses. Public being usable to communicate on an internal network and the internet, whereas private addresses can only communicate on their own network unless they're combined with something like NAT to allow them to access the internet. I hope this has been informative for you, and I'd like to thank you for viewing.